All right, 7.1, modeling situations with differential equations. So we're in the f prime world. So we're in the derivative graph. So we're thinking of not regular, but now we're in the derivative, no? So think that everything's about the graphs is going to be derivative. All right, so the rate of change, we're looking at the rate of change of A with respect to something, how something changes with respect to something else. What does A represent in this situation? Well, after we do it, then I'll give you what it represents. The rate of change of A with respect to what? Usually is T, no? So with respect to time, is proportional to R. So this is kind of like how they do, they've been doing modern mathematics. It's basically, so how do you write down this situation that's saying that the rate of change of A? So we're using, I think this is called Leibniz notation, not F prime, but DD. The rate of change of A, DDA, with respect to T is equal to, see, the rate of change of A with respect to T is proportional to R. So the rate of change of A with respect to T is proportional to R. Proportional means that A gets bigger because R gets bigger as time changes, or the area gets smaller if the R gets smaller as T gets, I guess it's going backwards, but it's the rate of, so this is going to be T. No, this is not going to be T, it's going to be what goes here? R. So the dA dt is equal to R, and we need a constant of proportionality, a letter for this. We're going to do the rate of change of A with respect to T is proportional to R. Let's use K. So dA dt is equal to K times R. That's what that means. That's how you read this. The rate of change of A with respect to T is equal to K times R. Let's see. All right. So let's do another one, number 2. So the rate of change, again, this is all rate of change. The rate of change of Y with respect to, so the rate of change of Y with respect to, so with respect to what? Again, we could do T, but what is it about in this situation? Is with respect to X, because that's what it's respect to. To X is proportional to, so the rate of change of Y with respect to X is proportional to Y. So how do we interpret it? What does this mean? The rate of change, so we're going to do dd. So the rate of change of Y with respect to X is proportional to Y. So the rate of change of Y with respect to X is proportional to Y. This is exponential. This is like what we're going to use a lot in this chapter. This equation right here. Dy dx is equal to ky. All right. Next, 3. The rate of change of G with respect to, the rate of change of G with respect to what? Again, what to respect to what? Is it X? Is it Y? Is it T? The the rate of change of g with respect to t, back to time. So how g changes as time changes is proportional to the square root of g. So the rate of change, how do you write this down? The rate of change, dd, the rate of change of g with respect to time, is proportional to the square root of g. So it's proportional to the square root of g. And then k again here, the constant of proportionality. The rate of change of g with respect to t is proportional to the square root of g. Let's do one more, last one. For the rate of change of p with respect to what? The rate of change of p with respect to, again, t, back to t. The rate of change of p with respect to t is inversely proportional. So here's another one, and I don't have an example. There's even another one. It's called jointly, but when it comes up on the homework, we'll go over that, I guess. The rate of change of p with respect to t is inversely proportional to the cube root of p. So this one's going to be dd, the rate of change of p with respect to t is equal to inversely proportional. What is inversely proportional? Inverse, like the inverse function, y equals what? 1 over x? So it's got to be at the bottom and not the top. So it's going to be what? Is inversely proportional to the cube root of p. Cube root of p. Cube root of p. And then put the k on top where it just... So directly proportional. These ones we've done is directly or just proportional, and this is inversely proportional fraction. Jointly proportional is when they're right next to each other. So we'll go over that later. There's that. dp dt is equal to that. Okay, that's chapter 7.1. Moving to 7.2 now. 7.2. Verifying solutions for differential equations. So differential equations, I just said that now we're in the derivative world. We're not in the regular algebra, x and y function graph. It's now in a graph that is differential. So differential equations contain n blank and one or more of its blank. The order of the differential equation is the order of that occurs in the equation. So differential equations contain what? Contain n. What does it contain? Contain an equation, an unknown function. Differential equations contain an unknown function. And one or more of its derivatives. So it's an unknown function. So here's exactly what I just said. We are in this derivative world and we don't know where it came from in its original function, because now we're just in the differentials. So the order of a differential equation is the order of the highest derivative that occurs in the equation. All right, so here, these are all going to mean the same thing. Here are examples of differential equations. Y double prime plus 2y prime equals 3y. This is a differential equation of a second order. Second order differential equation because the highest derivative is y double prime. So this is a second order differential equation. F double prime of x plus 2 times f prime of x equals 3y. It's the same one with the different notation. I think this first one is called Lagrange or whatever. This is whatever, I don't know who came up with these different ways of writing them down like this. But they all represent the same thing. This is the one I just said was, so it was who? Newton, then it was Leibniz. So this is Leibniz notation, and they all mean the same thing. Same differential equation written in a different form. The blank of a differential equation are the solutions of a differential equation. The solution are of equations that satisfy the differential equation. The solution of a different equation are the solutions of a different equation, differential equation are the infinite, or what is it? Are what? An infinite family. The solutions of a differential equation are an infinite family of equations that satisfy the differential equation. So no longer are we solving simple equations like 3x equal to 12 or something, where this has a unique solution. This is algebra, divided by 3x equal to 4, so it has a unique solution here. Now here, these differential equations have infinite solutions. The solutions of a differential equation are infinite family of equations. All right, so let's do some problems dealing with this. Here we go. So here's problem 1. Find the particular solution that passes through the given point for the following differential equations. Look, okay. So this is a derivative already. It's linear. dy dx equals 4x plus 2. It's already a derivative. So what would it be? It's a solution of it. If this is already a derivative, if we want it to go back to be y equals something, it would be what? This is already a derivative of something. It became linear, no? So what's would be an antiderivative of it? Wouldn't it be a quadratic? Because the derivative of a quadratic is a linear function. So let's go. Let's do this. So how do we solve this and figure it out? So this is the way we do it. We separate the variable, the dy. So what we're gonna do is do this. See up here on the right side, we only got x variable, 4x plus 2. So we're gonna move this dx over to the other side. So what I'm gonna do is do this times by dx here. I'm gonna times this by dx. So let's go ahead and do that. So it'd be dy equals 4x plus 2 dx. And then I'm going to integrate this. What's the integral of dy? It just be y. I'm gonna go like this: y plus some c. Let's just go. Let's go. Some constant. What's the integral over here on this side? Come on. 2x squared. Plus 2x plus what? 2x plus c. See, we got some constants here, and it's just constant. This could be constant 1 and constant 2, and then we can subtract the constants. So at the end of the day, it's just going to be one constant. So you could say constant equals constant 1 minus constant 1. Let's see, minus constant 1. So we can say that constant equals constant 2 minus constant 1. And they're all just numbers, so a bunch of constants. So at the end of the day, we usually just kind of don't even write down this right here, and we're more concerned about that constant over there. So it was y plus constant 1, and then this right here, constant 2. But at the end of the day, maybe we're just concerned on this, the dx1 constant. So let's just go like that. Hopefully you understood what I'm saying. These are a bunch of constants, and constant, whatever that constant is, and with that constant, we create another constant. So it's just a constant. All right. How do I figure out what this constant is? How do I figure out what that constant is? Don't I plug in x and y? So what is C? And so what is that particular equation for this differential equation? It will be, now that we figured out what C is, it will be this. Y equals 2x squared plus 2x plus 3. All right, let's do one more. All right, let's go number 2. So again, we notice that on the right side, it's all x's. So we're going to separate the dx, put it on the other side. So we're going to have dy is equal to e to 2x minus 2x squared dx So the integral of dy is what? So we're just going to put y and not put the plus c or anything like that because it's a bunch of c's. And at the end, all the c's, you can just combine them to be something. So the integral of e to the 2x, what's the integral of e to the 2x? E to the 2x over 2, yeah. Or 1/2 e to the 2. And then what? Then what? I'm plugging x and y. Find c. You want to find c? 0 e to the 0 power is what? E, that's 1. 1/2. So 4 equals 1/2 plus c. So c is equal to what? 3.5, which is 7/2, no? So we got that c. You plug it in here. It's going to be y equals e to the 2x over 2 minus 2/3 x cubed plus 7/2. Goes number 3. In the following problems, verify that the given answers are solutions of the differential equation. So this is the differential equation here. And we want to check, is this a solution of it? So how do you, it goes back to algebra, no? So somebody says y equal to 3x plus 4, and they ask you, is the point 1, 0 a solution? What do? Don't you just plug it in, x and y, plug them in? It doesn't make, is the left equal to a right, and yes or no? Yes? That's what we do, no? So there's the same idea here, but we don't just have numbers, we're gonna have to get these other things. So definitely we got what? Let's go over here. So we got 2 times y. We do have y. What is y? This thing, no? So 2 times 3 e to the negative 2x equal to 0. But we need to get y prime, no? We need to get what this y prime is. So how do I find y prime? How do I find y prime? Don't you just take the derivative of this? So I can take y prime, no? Y prime, and then whatever that's going to be, we're going to put it here. So what's y prime? Y prime is going to be what? Oh, taking the derivative of it, no? So it's going to be what? So then y prime, we're going to put it here. Is it true? I don't have to do anything more. 2 times 3 is 6. 6, we're check. Okay, here's the last one for today. So we're going to check 2 different functions, see if they are solutions of the differential equation here. Let's do it for this one first. So here, if I do it here, we got on the right side 9 times y, and y is this thing, so it'll be e to the 3x. So that's what we got on the right side. On the left side, we have to go all the way to the second derivative of the function. So what's y prime? 3 e to the 3x. What's y double prime? 9 So that's what goes here on the right, on the left side. 9 e to the 3x. Is it true? It's true, no? So now let's do it for this one. So 9 e to the 3x, and then we got to do it here on this one. So this is going to be y prime is what? Negative 3 e to the negative 3x. And y double prime is what? Oh no, here a second. Is it true for this one over here? No, because it's negative 3x and 3x is not the same. So that's a no. Let's see what happened here. Was it a no on the other one? Let's see. Look. Because the exponent was not the same. Oh, what the heck? Hold on.
You wrote it wrong.
I wrote it wrong?
You wrote it wrong.
Let me go back to it.
You put the first y. You wrote it wrong somewhere.
9. Oh, look. 9 and y is. Yeah. So it's true, no? It was true. All right, that's it. We're done.